All right, chapter 2 is called The Nature of Matter, and we're going to go through section 2.1 today. Section 2.1 is called Different Types of Substances, and there is a separate presentation for this set of notes, Phases of Matter Gilliland, so that will be a different file that you will click on. The one we're going to do right now is another set of notes over different types of substances. So what is matter? Which statement about matter is true? Atoms are not matter, but they are contained in matter. Matter exists only when you can see it. Living things are not matter. Matter is made up of atoms. The correct answer is matter is made up of atoms. There are 3 physical states of matter. You guys should know this by now: solid, liquid, and gas. In the solid state of matter, which is represented on the right-hand side, solid particles have the lowest amount of energy. The particles do not have enough energy to break apart from each other, and therefore solids have a definite volume and a definite shape. As we gain more energy in those particles, the particles are able to break free from the crystalline lattice of a solid, and they are able to slide past one another. So they have a definite volume. The volume does not change. If you have 50 milliliters of water in a cup, a rectangular or square cup, and you pour it into a cylinder, the volume stays the same. So that's what definite volume means. Because the particles in the liquid have more energy, though, they will take the shape of their container because they have that energy to move and slide past each other. As you add more energy to a solid, the particles gain enough energy to break free from their structure, and they turn into the gas state. So gases take the volume and shape of their container. The changes of state between the solid, liquid, and gases have specific names. When you go from a solid to a liquid, it refers to melting. So you are adding energy to turn the solid particles into liquid particles. Evaporation, you add energy from a liquid, the particles gain enough energy to turn into the gas phase. And these names right here, those are called phase changes. Okay. Condensing, so melting and evaporation require the input of energy. Condensing goes the opposite way. So if you take energy away from a gas, you cool it down, the particles lose their energy and they turn into the liquid phase. If you take more energy away from that liquid, the particles lose that energy and turn into solids. So melting and evaporating requires the input of energy. Condensing and freezing requires the taking away of energy. Sublimation. Sublimation is a term that refers to the phase change directly from a solid into a gas. The most popular or common example of sublimation is dry ice or CO2, where it goes directly from a solid to a gas at negative 79 degrees Celsius. And oftentimes I get the question, is there a name for the opposite from a gas directly into a solid? And there is, and I don't know if it comes up on this PowerPoint, but it is called the phase change deposition. This is an example of a heating or cooling curve for water. Notice a couple of interesting things in this graph. Where the temperature rises, here, here, and here, is where you have your pure solid, liquid, or gas state. So here, where the temperature is increasing, you are all solid. This space right here, you would be all liquid, and then this space right here, you would be all gas, which means that at the flat places, that is where the phase changes are happening. So ice remains ice. It gains energy, its temperature increases until the very first piece of ice turns into water, and that occurs at 0 degrees Celsius. When that very first solid piece of water or ice turns into water, notice that the temperature stays a constant 0 degrees Celsius. So in that range right there, you have a mixture of both ice and water. So during the phase change between solid and liquid, notice that the temperature stays the same. As soon as that very last piece of ice melts into the last drop of water, turns into 100% water, you have completed the phase change, and then the temperature will start increasing again. All of the energy, so the question is, well, why doesn't the temperature increase at that point if you're still adding energy? The reason being is that all the energy at this point right here is going into breaking bonds. So there's no temperature increase during those phase changes. Notice the same thing happens over here for the water and steam. It remains water all the way up, liquid water, all the way up until 100 degrees Celsius. When the very first drop of water turns into steam at 100 degrees Celsius, we begin our phase change. Notice that the temperature stays the same. You have a mixture of both water and steam there. All of the energy that is being put into this time right now, or into that time, is being used to break bonds again. Okay, and then once the very last drop of water has turned into 100% steam, the temperature starts to increase again. The same is true for the opposite way. As you go from steam to water, when you are taking that energy away, when the very first piece of steam turns into water, you will have that phase change here. Notice the temperature does not change if you are going the opposite way as well. Okay, these arrows kind of just show you some important parts to this. It's called a heating or cooling curve, or a phase change diagram. You have water here at the increase, phase change of water and steam at that flat plateau, and then 100% steam. Notice the temperature increases again there. Mixtures. So a mixture is a substance, a mixture that has a substance dissolved in another substance is called a solution. Examples of solutions are salt water. You have NaCl, which is called a solute, mixed with water, which is called your solvent. So it is a mixture of two things dissolved in each other. Soda is an example of a solution. You have sugar and CO2. Those are your solutes, dissolved in water, which is your solvent. The solvent is always the larger part of the mixture. The solute is always the smaller part that is being dissolved into the solvent. A mixture that has a substance that isn't completely dissolved, where the particles are suspended, is called a suspension. Examples of suspensions include orange juice. So if you have orange juice, you have pulp, solid pieces of orange that are in that liquid orange liquid part. So you have to shake the orange juice up, or the particles will settle to the bottom. That is an example of a suspension. So suspensions are things where the particles are big enough that they will settle to the bottom if given time. You have to shake a suspension up in order for it to mix together. Italian salad dressing, like in this picture, is another example of a suspension. All those herbs and spices have to be shaken in order to dissolve. And if you don't shake it and let it sit, those particles drop to the bottom. And that is an example of a suspension. How do solutions differ from pure substances? Okay, so salt water is a solution. It is made up of salt and water. So this is a heating curve for the solution of sodium chloride or salt water. Here on the right hand side is a similar heating curve, but this is for pure water. So there is no salt or any impurity. So here there is no impurity, and when I say impurity, I'm referring to salt in the salt water's case. There is no impurity in pure water. So what differences can be determined based on these graphs? If you look at the salt water, notice that there is a gradual kind of curve up to about 100 degrees. It actually starts increasing between sort of increasing at like 95 or so. And then there is a gradual incline past 100 degrees. Notice for pure water, you have a pretty straight curve, and that at 100 degrees, it does a sharp plateau to show the phase change. So one difference that you might be able to recognize is that for pure water, there is a very definite sharp phase change that occurs at 100 degrees Celsius. For salt water, there's a more gradual change that occurs in the range of 95 to 105 degrees Celsius. So salt water gradually climbs during boiling. Pure water has a constant temperature at boiling. Salt water's boiling point is higher than that of pure water. Let's take a look at freezing. So if we take a look at the freezing point graph for pure water versus salt water, the pure water is this black line, and the salt water is the red line. Okay, so again, we see that the salt water freezes at a lower temperature than 0 degrees Celsius for pure water. Pure water also is a constant temperature. The red line for the salt water sort of has a gradual decrease. For pure water, it has that similar sharp freezing point at 0 degrees Celsius. So, why do solutions freeze and boil differently? First, let's take a look at pure water. In pure water, we have all water molecules. All these blue dots right here represent water molecules. Okay? The atmosphere pressure keeps the water from escaping. So there is pressure being pushed down onto these particles. It keeps those water particles in. Increasing heat causes more energy in the water, which causes an increase in pressure. So the particles eventually have enough energy to break free from that water structure and boil. So boiling occurs when the atmospheric pressure equals the pressure in the beaker. And the particles start to come out of solution. Now, if we take a look at salt water, the blue particles represent the water. The impurities of salt are represented with the red dots. Again, boiling occurs when the atmospheric pressure equals the pressure inside the beaker. Water still needs the energy, but needs more energy to break the attraction from the salt. So in other words, the impurity makes it harder for these blue water molecules to break free from that structure. Okay, so it takes a higher amount of energy in order to boil, in order to break free from those red circles that are sort of holding the blue circles in their structure. Whoa. Somehow I skipped all the way down here. So let me go back to where I was here. Don't know how that happened. Okay, so water still needs energy, but it needs more energy to break attraction from the salt. Therefore, it occurs at a higher temperature. So this question may appear on your test. What does an impurity do to the boiling point? If you have an impurity, such as salt, it is going to increase the boiling point of the solution. In a similar fashion, an impurity will lower the freezing point, like we saw in the previous slide, of um, a pure solution. Okay, so here, same concept for freezing. Water molecules form a bond to crystallize. Salt molecules interfere with water's bonding, therefore need a colder temperature to form a solid. So in other words, what you need to take away from this slide is that an impurity such as salt is going to lower the freezing point of the water, of the pure solution. Okay. And we will stop there for this section.